Hello students, welcome to this new video presentation on gravitation part 3 given in chapter number 8 of physics for class 11. In today's lecture, I will brief about Earth satellites, energy of an orbiting satellite, geostationary and polar satellites, and finally we will end this chapter number 8 with the discussions on weightlessness. As you all know, Earth satellites are objects which revolve around the Earth. Their motion is very similar to the motion of planets around the Sun. Hence, Kepler's law of planetary motion are equally applicable to them. In particular, their orbits around the Earth are circular or elliptical. Moon is the only natural satellite of the Earth with a near circular orbit with a time period of approximately 27.3 days, which is also roughly equal to the rotational period of Moon about its own axis. Since 1957, the advances in satellite technology have enabled many countries, including India, to launch artificial Earth satellites for use in telecommunication, geophysics, and meteorology. We will study about satellites in this session. Some of the chapters or section are having extensive use of formulae which we have studied in the previous session. Please go through it, revise it. The links are given in the description part of this video. I welcome you once again. Wherever I am going fast, please pause it and note down the important points. Earth satellites. Earth satellites are the objects which revolve around the Earth. Consider a satellite in the circular orbit at a distance of Re plus h, where Re is the radius of the Earth and h is the height of the satellite from the surface of the Earth. If m is the mass of satellite and v is its speed, then the centripetal force required for this orbit is given by the relation F centripetal is equal to mv square by Re plus h. Let it be equation 1. This centripetal force is provided by the gravitational force which is directed towards the central. That is, the centripetal force is directed towards the central. Therefore, F gravitational is given by the relations F gravitational is equal to G into M into capital ME divided by RE plus H whole square. Here capital G is the gravitational constant, small m is the mass of satellite, capital ME is the mass of Earth and RE is the radius of Earth plus H is the height of satellite above the surface of the Earth. Let it be equation 2. Equating equations 1 and 2 above and cancelling m and in the numerator and Re plus H in the denominator, we get V square is equal to G into capital G into ME divided by Re plus H. Let it be equation 3a. If you put H is equal to 0, that is that the very surface satellite very close to the Earth as compared to the radius, we get V square is equal to G into ME divided by Re. That will be equal to G is equal to Re because small g, that is the acceleration due to gravity, equals G into ME divided by Re square. Let it be equation 3b. In every orbit, the satellite traverses a distance of 2 pi into RH because we know that the circumference of the circle, which is the orbit of the satellite, is given by 2 pi into Re plus H and its speed is given by distance traveled over time taken, that is V is equal to 2 pi into Re plus H over T. Therefore, its time period t is given by t is equal to 2 pi into Re plus h divided by V. Substituting for V from this equation, we get from equation 3b, we get t is equal to 2 pi into Re plus h whole to the power of 3 by 2 divided by square root of g into me. Please substitute for v square from equation 3b and you can simplify this equation. You will get this relationship 4a. Squaring both sides, we get this equation 4a, we get t square is equal to k into Re plus h whole cube. Let it be equation 4b. Here k is a constant equal to k is equal to 4 pi square divided by GME. That is this term and the denominator. Let it be equation 4c. Please note that in the equation 4b, this is the Kepler's law of periods which we have studied in the previous video. And the link for the same is given in the description part of this video. Hence, 4b is the Kepler's law of periods as applied to the motion of satellites around the Earth. For a satellite very close to the surface of the Earth, h can be neglected in comparison to Re. That is, Re is far greater than h and h is 0. Hence, for such satellites, t is equal to t naught, where t naught is equal to 2 pi into square root of Re by g. You rewrite this equation and show that it is t naught is equal to 2 pi into square root of Re by g. Let it be equation 5. If we substitute the numerical values of radius of Earth, that is 6,400 kilometers, and acceleration due to gravity, that is small g, as 9.8 meters per second square, then we get the value of t naught is approximately equal to 85 minutes. Worked examples. Question number 1. The planet Mars has two moons, Phobos and Deimos. Part 1. Phobos has a period of 7 hours 39 minutes and an orbital radius of Phobos is 9.4 into 10 to the power of 3 kilometers. Calculate the mass of Mars. The first part is we have to calculate the mass of the Mars. Assume that the Earth and Mars move in a circular orbit around the Sun, with the Martian orbit being 1.52 times the orbital radius of the Earth. What is the length of Martian year in days? So please read the question again and again and we will solve it. Answer. Given the time period is given as 7 hours 39 minutes, that is equal to 459 into 60 seconds. And radius of Phobos is 9.4 into 10 to the power of 3 kilometers. That is equal to, converting kilometers into meters, 9.4 into 10 to the power of 6 meters. Therefore, we know that t square is equal to kr cube. For applying for the Mars, we get k is equal to 4 pi square divided by capital G into mm. That is equal to m suffix m is equal to 4 pi square divided by g into r cube by t square. Therefore, putting the values as 4 pi square is 3.14 whole square divided by gravitational constant is 6.67 into 10 to the power of minus 11. R is 9.4 into 3 into 2 to the power of 6. Whole cube is 9.4 whole cube into 10 to the power of 18 divided by mm is 459 into 60 whole square. Therefore, that becomes 6.48 into 10 to the power of 23 kgs. Now applying Kepler's third law, we get T. We know that formula Tm square by T square is equal to Rms whole cube divided by Res whole cube. Here Tm is the time period of Mars and Te is the time period of Earth. And RMS is the Mars sun distance and RES the Earth sun distance. So this is the simplifying, and it is given the ratio of T of the ratio of the radiuses is 1.52 times. 1.52 times the radius of the Earth. Therefore, putting the values, Tm is equal to 1.52 into to the power of 3 by 2 into 365. That becomes 684 days. Please note that the orbits of all planets except Mercury, Mars, Pluto are very close to being circular. That means they are approximately circular. In case of Earth, the semi-major axis is A and semi-minor axis is B, and their ratio is 0.99986. Next question. We have to find the weight of the Earth. You are given the following data. G is equal to 9.81 meters per second square. Radius of Earth is 6.37 into 10 to the power of 6, and the distance to the moon is 3.84 into 10 to the power of 8 meters, and the time period of moon's revolution is 27.3 days. Obtain the mass of Earth ME in two different ways. Please read the question again and again and interpret it, and I will proceed with the solution. Given values are written here. G is equal to 9.81 meters per second. Earth's radius is 6.37 into 10 to the power of 6 meters, and R is given as the distance of moon to Earth is 3.84 into 10 to the power of 8 meters, and the time period of moon's revolution is 27.3 days. So from this data we will apply G is equal to force by M, that is equal to G into capital ME divided by RE square. Therefore, rearranging, ME is equal to small g into RE square divided by capital G. Substituting the values, we get G as 9.81 into 6.37 into 10 to the power of 6 whole square divided by the value of gravitational constant capital G is 6.67 into 10 to the power of minus 11. This you have to remember, the value of capital G. Therefore, that simplifying, we get the value of ME, mass of the Earth, as 5.97 into 10 to the power of 24 kg. There is another method. The moon is a satellite of Earth. From the derivation of Kepler's law, we can apply the formula T square is equal to 4 pi square divided by capital G into capital M suffix E R cube. So therefore ME is equal to 4 pi square divided by G into T square, that is cross multiplying here, into R cube. Therefore ME is 4 into 3.4 into 3.14 into 3.84. It is given the radius, the distance of the moon and Earth is 3.84 whole cube into R to the 10 to the power of 24. Gravitational constant is 6.67 into 10 to the power of minus 11, and T square is 27.3 days converted into seconds, 60 into 60, and days are 24 hours. So it is given here. You write down, and the value will be, you will find that ME, mass of the Earth, is 6.02 into 10 to the power of 24 kgs, which is almost nearly equal to the value we found in the previous case. Energy of an orbiting satellite. Consider the equation V square is equal to G into ME divided by RE plus H, where V is the velocity, G is the gravitational constant, ME is the mass of Earth, and RE is the radius of Earth, and H is the height of an object above the surface. The kinetic energy of the satellite in a circular orbit with speed v is given by the relation fundamental equation kinetic energy is equal to half mv square. Here we substitute the value from the above equation. Hence kinetic energy is G into me divided by 2 into Re plus H. Let it be equation 1. Considering the gravitational potential energy at infinity to 0, that is if potential energy equal to 0, then the potential energy at a distance Re plus H from the center of the earth is given by the relation Pe is equal to minus G into M into Me divided by Re plus H. This is the equation of potential energy. Let it be equation 2. The kinetic energy is positive. Please examine the equation 1. Here the kinetic energy is positive and potential energy is negative, as shown in the figure. Here you see the y-axis is the energy and x-axis is the distance or radius r, the distance r. Hence the plot of potential energy potential energy is u here in the bottom, and kinetic energy is k at the above in the first quadrant. However, the magnitude of kinetic energy is half of P. Please see here it is divided by 2. Therefore, kinetic energy is half of potential energy. So that the total energy E is given by total energy is sum of kinetic energy plus potential energy, that is equal to, if we add equation 1 and 2, we get E is equal to, that is total energy is equal to capital G small m into capital Me divided by 2 into Re plus H. Let it be equation 3. The total energy of a circular orbiting satellite is thus negative. Hence, the total energy is negative and shown in this figure, the graph as E. This is the graph of E, with the potential energy being negative but twice its magnitude of the potential positive kinetic energy. When the orbit of a satellite becomes elliptical, both kinetic energy and potential energy vary from point to point. This is also shown in the graph. It is varying from point to point. The total energy, which remains constant, is negative as in the circular orbit case. Satellites are always at finite distance, that is a definite distance from the earth. Hence their energies cannot be positive or zero. So energies will never be positive or it will never touch the zero axis, x-axis. Now we will take up some work examples. Question number 3. Express the constant k, small k of equation k is equal to 4 pi square by gm in days and kilometers. Given k is equal to 10 to the power of minus 13 s square per meter cube. The moon is at a distance of 3.84 into 10 to the power of 5 kilometers from the earth. Obtain its time period of the revolution in days. Please read the question once again and interpret it. Let us solve it. Answer. It is given that k is equal to 10 to the power of minus 13 s square into m to the power of minus 3. You see above. Therefore, we have to convert this seconds into days if you want to convert into days, and hence it has to be divided by 60, that is seconds into minutes and minutes into hours. Therefore, it is 10 to the power of minus 13 1 over 24 into 60 whole square, because s square here, into days. This is converted, seconds is converted into days. Hence it is d square. And m to the power of minus 3, we have to convert meters into kilometers. Therefore, it is 1 over 1 into 1 by 1000 whole cube. That is m to the power of minus 3. It is, that is why 1 over 1000 whole cube. So that is meters converted into kilometers is kilometer 10 to the, into 10 to the kilometers minus to the power of minus 3. Therefore, simplifying, we get the answer as 1.33 into 10 to the power of minus 14 day squares per kilometer cube. Substituting the value of k in the equation, t square is equal to k into r cube. This equation you have to remember. K into r cube, we get t square is equal to, the value of k here is 1.33 into 10 to the power of minus 14 into r is given as 3.84 into 10 to the power of 5 whole cube. Therefore, t is equal to 27.3 days. Next question. Question number 4. A 400 kg satellite is in a circular orbit of radius 2 into RE, where RE is the radius of Earth, about the Earth. How much energy is required to transfer it to a circular orbit of radius 4 times RE? What are the changes in the kinetic and potential energy? Please read the question again. The weight of satellite is 400 kgs, which is normally at 2 into RE, twice the radius of Earth. But we are required to calculate what is the energy required to transfer this heat into a circular orbit of 4 times RE. What are the changes in kinetic and potential energy? Please read the question again and interpret it. Let me solve it. Initially, the E initially is equal to minus G into ME into small m divided by 4 times RE. And final energy will be equal to minus G into M into E of ME, mass of Earth, into small m divided by 8 times RE. So initially it was 2 RE, that is 2 into 2 RE is 4 RE, and our final energy is 2 into 4 RE, therefore 8 RE. The change in total energy is EF minus EI, that is given by delta E is equal to G times M into EM, ME into M divided by RE. I will read that. The change in total energy is G, capital G into capital ME into small m divided by 8 into RE. So therefore, delta E is equal to G into ME divided by RE square. This is the value of gravitation, G, small g, M into RE divided by 8. That is equal to delta E is equal to G. This is the bracket, the terms in the bracket is G and M as it is RE, radius of Earth. RE and RE get RE divided by 8. Therefore, delta E is equal to value of G is 9.81 and M mass is 400 kg, 400 into RE, radius of Earth is 6.37 into 10 to the power of 6 divided by 8. Simplifying, we get 3.13 into 10 to the power of 9 joules. Therefore, kinetic energy is reduced. Therefore, delta K is equal to Kf minus Ki. That is equal to minus 3.13 into 10 to the power of 9 joules. The change in potential energy is twice the change in total energy. Therefore, the potential energy is represented by V, capital V. Delta V is equal to capital VF minus capital VI, that is equal to minus 6.25 into 10 to the power of 9 joules. Geostationary satellites. The satellite which appears stationary relative to Earth, underline the word appears stationary relative to Earth, is called geostationary or geosynchronous satellite. It is also called the communication satellite. Please see the note here and the insert. We know that equation. Period of any satellite is given by t square is equal to 4 pi square divided by g into me into Re plus H whole cube. This we had derived in the previous sections. So if in this equation T is equal to 24 hours, which we obtained by adjusting the value of Re plus H, then and if the circular orbit is in equatorial plane of the Earth, such a satellite having the same period as the period of rotation of Earth about its own axis would appear stationary as viewed from a point on the Earth. Hence, a geostationary satellite always stays over the same place above the Earth. Please see the figure here below, image below here. This horizontal brown colored orbit is the geostationary orbit, or it is in the plane of equatorial orbit. The orbit of geostationary satellite is also known as parking orbit. It should revolve in an orbit concentric and coplanar with the equatorial plane. This plane is called equatorial plane and it should be concentric. That is, the center of this orbit and the center of the Earth should coincide, and its plane should also be the equatorial plane. Its sense of rotation should be same as that of Earth. Because Earth is also rotating, the satellite also should rotate in the same sense as that of Earth. Its period of revolution around the Earth should be same as that of Earth. That is, Earth revolves in 24 hours. Hence, both the satellite and Earth should revolve around the same period. Height of geostationary satellite from the surface of Earth is approximately equal to h is equal to 6 times r. It is about 36,000 kilometers. The orbital velocity of the satellite is v equal to 3.08 kilometers per second. Angular momentum of satellite depends on both the mass of the orbiting satellite and planet as well as the radius of the orbit. Therefore, summarizing, if T is equal to 24 hours as said earlier in the equation, T is equal to 2 pi into Re plus H whole to the power of 3 by 2 divided by square root of G into Me. This is by taking the square root of this equation given in the note, which is also given in the previous section 8.9. The height of geostationary satellite in such a case is given by h is equal to, rearranging the value of, for evaluating h, we get h is equal to 1 by 3 into square root of t square g me divided by 4 pi square minus Re. This term Re is also taken on the right hand side. That is equal to 36,000 kilometers. Geostationary satellites are used in radio, TV, and telephonic communications. Polar satellites. Please recall the image shown in the previous slide explaining the geostationary orbits. In this section, we will study about the polar satellites. Polar satellites revolve around the Earth in circles north to south orbit which passes over the north and south pole. Please see, this is a globe, this is a north pole and this is a south pole. The polar satellites revolve in the orbit shown in the blue color. These are also called sun synchronous or polar orbits. So, polar satellites revolve around the Earth in circles north to south, which passes over the north and south poles. Polar satellite, a strip on the Earth's surface shown in the shaded portion here, is visible from satellite during one cycle. For the next revolution of the satellite, the Earth has rotated a little on its axis, so that an adjacent strip becomes visible. The altitude of these satellites, polar satellite, is 500 to 800 kilometers. Angle of inclination of the orbit with equatorial plane is 90 degrees. You see here the blue colored orbit is at an angle 90 degrees from the equatorial orbit. They cross equator of the Earth daily at the same time. Hence, they are called sun synchronous satellites. The polar satellites are used for monitoring climate change, remote sensing, meteorology and environmental studies, spying and surveillance, etc. Weightlessness. Weight of an object is the force with which the Earth attracts it. We are conscious of our own weight when we stand on a surface, since the surface exerts a force opposite to our weight to keep us at rest. The same principle holds good when we measure the weight of an object by a spring balance hung from a fixed point, that is, for example, from the ceiling. The object would fall down unless it is subject to a force opposite to the gravity. This is exactly what happens when the spring exerts on the object. This is because the spring is pulled down a little by the gravitational pull of the object, and in turn the spring exerts a force on the object vertically downwards. Imagine that a top end of the balance is no longer held fixed to the top ceiling of the room. Both ends of the spring as well as the object move with identical acceleration g. The spring is not stretched and does not exert any upward force on the object which is moving down with an acceleration g due to gravity. The reading recorded by the spring is zero, since the spring is not stretched at all. If the object were a human being, he or she will not feel his weight, since there is no upward force on him. Thus, when an object is free to fall, it is weightless, and this phenomenon is called the phenomenon of weightlessness. Hence, consider a case when a human being falls freely. He or she will not feel the weight, since there is no upward force on him. Thus, when an object is in free fall, it is weightless, and this phenomena is usually called the phenomenon of weightlessness. Please note down this paragraph. In a satellite around the Earth, every part and parcel of the satellite has an acceleration towards the center of the Earth, which is exactly the value of Earth's acceleration due to gravity at that position. Thus, in the satellite, Everything is inside it is in state of free fall. This is just as if we were falling towards the earth from a height. Thus, in a manned satellite, people inside experience no gravity. The gravity for us defines the vertical direction, and thus for them there are no horizontal or vertical directions. All directions are same. Please note down. Pictures of astronauts floating in a satellite show this. You can view these astronauts photograph pictures in the net. The state of weightlessness or zero weight can be observed in the following situation. Number one, when the object falls freely under gravity, when a satellite revolves in its orbit around the Earth. Point number three, when bodies are at null points in the outer space. The zero gravity region is called null point. Now, we have completed our theory part of gravitation. In this section, we will take up questions of 2 marks. In the previous video, that is in part 2, we had solved questions of 1 mark. Let us start. A satellite revolves close to the surface of a planet. How is its orbital velocity related with the escape velocity of the planet? Please read the questions again and again and try to solve yourself. However, for your convenience, I am solving it. Answer. VE is equal to, that is escape velocity is equal to square root of 2 into V naught. Hence, where V naught is the orbital velocity. Therefore, VE is equal to square root of 2 into Gm by R, and V naught is equal to square root of Gm by R, where R is equal to capital R. Two satellites A and B are orbiting around the Earth in a circular orbit of the same radius of mass A. Same radius, the mass of A is 16 times that of B. What is the ratio of the period of revolution of B to that of A? Please read the question again. Answer. T is equal to, we know 2 pi r over V, where 2 pi r is the distance traveled and V is the velocity. So T is the time period. Therefore, V is equal to G into M by R, and T is independent of the mass. So whatever the mass, T does not change. Therefore, the ratio TB by TA is 1:1. That is, TB is equal to TA, because radius is same. Question number 7. Satellite does not require any fuel to orbit the Earth. Why? Answer. The gravitational force between satellite and Earth provides the necessary centripetal force for the satellite to orbit the Earth. Question number 8. If suddenly the gravitational force of the attraction between Earth and satellite becomes zero, what would happen to the satellite? Answer. The satellite will move tangentially to the original orbit with a velocity with which it was revolving. Question number 9. Why an astronaut in the orbit spacecraft is not zero gravity, although he is in weightlessness? The astronaut is in gravitational field of the Earth and he experiences gravity. However, the gravity is used in providing the necessary centripetal force. So, in the state of free fall towards the Earth. Question number 10. Is it possible to place an artificial satellite in an orbit so that it is always visible over New Delhi? Answer is no. A satellite will be always visible only if it revolves in the equatorial plane, but New Delhi does not lie in the region of equatorial plane. Question number 11. Write an important use of geostationary satellite and number 2 polar satellite. Geostationary satellites are used for telecommunication and polar satellites for remote sensing. Question number 12. If the radius of Earth were to decrease by 1%, keeping its mass same, how will the acceleration due to gravity change? We know the answer. G is equal to G into m by r square. If r decreases by 1%, that is, it becomes 99 by 100 of r. Therefore, G dash will be equal to Gm divided by 0.99 into R. That is, new R is 0.99 R whole square. That is equal to 1.02 into Gm by R square. Therefore, G dash increases by 0.02 Gm over R square. Therefore, it increases by 2%. So, if the radius decreases by 1%, the acceleration due to gravity increases by 2%. Question number 13. A satellite is moving around the Earth with a velocity v0. What should be the minimum percentage increase in its velocity so that the satellite escapes? Answer. The maximum orbital velocity of the satellite orbiting near its surface is given by v0 is equal to square root of g into r minus ve divided by root 2. For such satellite to escape gravitational pull, the velocity must become ve. Therefore, ve should be is equal to square root of v0, square root of 2 into v0. Square root of 2 is 1.414 into v0. That is 1 plus 0.414 into v0. So that means it has to increase by 0.414 in 1 or 41.4%. The minimum increment is required as the velocity of satellite is maximum when it is nearer the Earth. Question number 14. The radii of two planets are r and 2r respectively, and their densities are rho and rho by 2 respectively. What is the ratio of acceleration due to gravity at their surfaces? Here, the acceleration due to gravity g is proportional to r into rho, where r is the radius and rho is the density. Therefore, g1 by g2 is equal to r into rho divided by 2 into r into rho by 2, because for the second satellite, the radius is 2r and density is rho by 2. So, simplifying, the ratio is 1:1. Question number 15. If the Earth has a mass 9 times and radius 4 times than that of a planet P, calculate the escape velocity at the planet P if its value on the Earth is 11.2 kilometers per second. Please read the question again and I will solve it. We know V is equal to, that is velocity of Earth is equal to square root of 2 into g me divided by re, and velocity of planet is Vp is equal to square root of 2g into mp divided by rp. Therefore, mp is equal to me divided by 9. So, me divided by 9 it is given, and rp is equal to re divided by 4. That is, the mass of planet is 9 times of mass of Earth, equal 9 times the planet's mass, and radius is 1/4 of Earth's radius. Therefore, Vp is equal to 2gm by 9 divided by Re by 4. Simplifying, we get is 7.47 kilometers per second. Next question. At what height from the surface of the Earth will the value of G be reduced by 36% of its value at the surface of the Earth? Answer. Now, G is reduced by 36%. That means the gravitational force will be 64% of G. That is equal to 64 by 100 G. Therefore, G dash is equal to G into R square by R plus H square. So this term is nothing but 64 by 100 into G. Therefore, R by R plus H is equal to 8. Square root of 64 is 8 and square root of 100 is 10. So therefore, H is equal to, simplifying, we get R by 4, that is equal to 1600 kilometers. Next question. At what depth is the value of G same as at the height of 40 kilometers from the surface of the Earth? So GD should be equal to GH. Therefore, G into 1 plus 1 into D by R is equal to 1 into 2H by R. Therefore, D is equal to 2H. Here comparing the ratios of numerator, we get D is equal to 2H. That is equal to 2 into 40 kilometers, 80 kilometers. Question number 8. The mean orbital radius of the Earth is around the Sun is 1.5 into 10 to the power of 8 kilometers. Calculate the mass of Sun if G is equal to 6.67 into 10 to the power of minus 11 Newton meter square per kg. Therefore, R is equal to 1.5 into 10 to the power of 8 kilometers. That is equal to 1.5 into 10 to the power of 11. That is converting kilometers into meters. Therefore, T is equal to 365 days. That is equal to 365 into 24 into 3600 seconds. That is converting days into seconds. And centripetal force is equal to gravitational force. Therefore, mv square by r is equal to g into m by capital M into small m by r square. Therefore, m by r into 2 pi r divided by t whole square is equal to g of capital M small m divided by r square. Therefore, ms is equal to 4 pi r pi square r cube into gt. Therefore, ms is equal to 4, substituting the values, 4 into 9.87 into 1.5 into 10 to the power of 11 whole cube divided by 6.64 into 10 to the power of 11 into 365 into 24 into 3600 whole square. Simplifying, we get 2.01 into 10 to the power of 30 G. That is, G is grams here. Question number 19. Draw graphs showing the variation of acceleration due to gravity with height above the Earth's surface and to below the Earth's surface. So the graph is shown in the figure. G is proportional to 1 by r square. That is the distance. So for r greater than 0, this is on the right hand side. Above the surface, it is AB. And for G proportional to R by R minus D, for R less than 0, that is on the left hand side, this is the origin. On the left hand side, below the surface of the Earth, it is AC. G is maximum for R is equal to 0. So the gravitation, acceleration due to gravity is maximum on the surface. Next question. A rocket is fired from the Earth towards the Sun. At what point on its path the gravitational force on the rocket is zero? Given that mass of Sun is equal to 2 into 10 to the power of 30 kgs, mass of Earth is equal to 6 into 20 to the power of 4 kg, neglect the effect of other planets, and it is also given that orbital radius is equal to 1.5 into 10 to the power of 11 meters. Therefore, write down the given parameters as shown. Let m be the mass of rocket. Let at distance x from the Earth the gravitational force on the rocket be 0. Then at this distance the gravitational pull of Earth equals the gravitational pull of Sun. Hence equating, we write g into me into small m divided by x square. Here me is the mass of Earth, that is equal to g into ms into m divided by r minus x square. So here ms is the mass of Sun. So simplifying, we get r minus x is divided by x is equal to square root of ms by me. That is equal to 5.77 into 10 to the 5.77.35. 3 minus, therefore r minus x is equal to 577.35x. That is cross multiplying the extremely left side terms with the last term. Therefore r minus x is equal to 577.35x, or x is equal to 2.59 into 10 to the power of 8 meters. Please write step by step and you will understand very clearly. I am just going fast. Question number 21. If the Earth is one half of its present distance from the Sun, in how many days will be the present 1 year on the surface will change? That is, the distance of Earth from the Sun is reduced by half. Answer. So it is given T1 is equal to 365. R1 is equal to R. T2 is what if R2 is R by 2. That is, it is reduced by half. Therefore, T2 square by T1 square is equal to R2 cube by R1 cube. Therefore, T2 is equal to T1 into R2 by R1 into to the power of 3 by 2. Simplifying, substituting the values, 365 into R by 2 divided by R into 3 to the power of 3 by 2. Here, the R2 is R by 2. That is equal to 129. If the distance from Sun is reduced by half, the year will be 129 days. Therefore, the decrease in number of days in 1 year will be 365 minus 129 is equal to 236 days. Next question. A body weighs 63 newtons on the surface of the Earth. What is the gravitational force on it due to Earth at a height equal to half of the radius of the Earth? So given mass weight is mg, that is equal to 63 newtons, and height is r by 2, half of its radius. Therefore, gh divided by g is equal to r by r plus h whole square. Because height is reduced by half and it is equal to half of the radius, it is the right hand side term is r by r plus r by 2 whole square. That is equal to 2 by 3 into 2 by 3 whole square. That is equal to 4 by 9. Therefore, height GH will be equal to 4 by 9 of G. Therefore, M into GH, the weight will be M into GH will be equal to M into 4 by 9 into G. That is equal to M is 63 newtons given into 4 by 9. That is equal to 28 newtons. Next question. Why the space rockets are generally launched west to east? Answer. Since the Earth revolves from west to east, so when the rocket is launched from west to east, the relative velocity of the rocket increases, which helps it to rise without much consumption of fuel. Next question. Explain why a tennis ball bounces higher on hills than in the plain. Answer. The value of G on the hills is less than the plain. So the weight of tennis ball on the hills is lesser force than at plains. That is why the earth attracts the ball on its hills with lesser force than at plains. Hence the ball bounces higher. Next question. The gravitational force on the earth due to sun is greater than moon. However, tidal effect due to moon's pull is greater than the tidal effect due to sun. Why? Answer. The tidal effect depends inversely on the cube of the distance, while the gravitational force depends on the square of the distance. Next question. The mass of moon is m by 81, where m is the mass of earth. Find the distance of the point where gravitational field due to earth and moon cancel each other. That is, they are equal. Given that the distance of the moon from the earth is 60 times r, where r is the radius of the earth. Answer. Gravitational field at C due to earth is equal to gravitational field at C due to moon. Therefore, Gm by G into m divided by 60 r minus x whole square is equal to Gm by 81 divided by x square. Therefore, 81 x square is equal to 60 r minus x whole square. Therefore, 9x equals 60 r minus x, taking the square root on both sides. Therefore, x is equal to 6r. This diagram, the relationship are shown in the figure above. With this, we come to the conclusion of part 3 of chapter 9. There are some more problems of 3 marks or 5 marks which we will be adding in our supplementary video. Next video we will take up on mechanical properties of solids part 1 chapter 9. Till then, goodbye.